Hello there, and welcome to your nightly deep dive into the science of sleep. Tonight, we turn our attention to something that fills the universe, yet has never been seen. Something that outweighs every star, every planet, every grain of dust, and every drifting atom of gas that has ever been catalogued or observed by every telescope ever built, and yet leaves no trace of light, no shadow, no color, no warmth. Dark matter is everywhere. It is threading through the room where you lie right now, passing through your body and the walls and the ground beneath you in an invisible, continuous river, as untouched and untouching as a ghost of the universe itself. It passes through the densest rock, through the iron heart of the earth, through the burning plasma of stars, without slowing, without leaving any mark. It is the invisible architecture on which everything visible is built, the scaffolding behind the stars, the hidden skeleton of galaxies, the dark framework on which the luminous universe is hung. It is the reason galaxies hold together, the reason the cosmic web has the shape it does, the reason stars exist at all. It is the hidden majority of all that exists. We have known it is there for nearly a century, and we still do not know what it is. That mystery, that particular combination of absolute certainty about its presence and genuine ignorance about its nature, is one of the most beautiful things in all of science. The knowledge that the universe is mostly made of something we have not yet understood, something patient and pervasive and ancient and quietly waiting across every scale and every epoch to finally be known. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, let this be the only thing asking anything of you. Let your body settle into wherever it rests, and let your breathing slow to something easy and unhurried. The day is behind you. The thinking and the doing and the deciding are done for now, set aside in the way that a weight is set down after a long carry. Let your shoulders drop a little further than they already have, and let your eyes, if they are not already closed, grow heavier with each slow and easy breath. There is nothing here that requires alertness or readiness or attention of any particular kind. We are going somewhere invisible tonight, somewhere vast and hidden and endlessly fascinating. And the only thing you need to do is let the words carry you, the way a current carries something placed gently in a river. Let your thoughts loosen their grip on the ordinary world and drift a little further apart with each breath. Let the quiet deepen until it fills the space that the day's noise has vacated. Let the dark matter flow through you, ancient and unhurried and constant, as it has always done. Let's begin. Dark matter is not dark in the ordinary sense. It is not a dark cloud or a dark region of space, the way that a storm cloud is dark, not a void or an absence or a place where something used to be and is no longer. It is dark in a far more radical sense. It does not interact with light at all. It does not emit light, the way that a star emits light by converting nuclear energy into photons. It does not absorb light, the way that a cloud of gas or dust absorbs certain wavelengths and creates the dark lines we see in stellar spectra. It does not reflect light, the way that a planet or a moon reflects the light of its parent star and becomes visible to us across the void. Dark matter is invisible, not because it is far away or too faint or obscured by something else, but because it has no relationship with light whatsoever. The photons that make up all electromagnetic radiation, from radio waves to gamma rays and everything in between, simply pass through dark matter as though dark matter were not there, because to photons, it is not there. It is a form of matter that exists in a kind of parallel relationship with the stuff we are made of, present in the same places, subject to the same gravitational rules, but otherwise completely disconnected from everything we can see or touch or measure directly. The universe we can observe with our eyes and our telescopes and our detectors of every kind represents, according to the best current measurements, only about 5% of all the matter and energy in the cosmos. Dark matter represents roughly 27%. The remaining 68% is dark energy, an even stranger phenomenon we will leave for another night. What makes this so fascinating is that 5%, the ordinary matter, the atoms and ions and molecules that make up stars and planets and people and everything we have ever directly detected, is not the normal state of the universe. It is the exception. It is the thin, luminous skin on an invisible ocean of something else entirely. Every galaxy we have ever seen, every nebula and cluster and filament of cosmic structure, is built within and upon a framework of dark matter that dwarfs the visible component in mass and volume. We live inside a structure we cannot see, like organisms that can perceive only the foam on the surface of a deep and invisible sea. We live inside a structure we cannot see, like organisms that can perceive only the foam on the surface of a deep and invisible sea. The implications of this for cosmology are profound and are still being worked through. Because dark matter does not interact with light, we cannot map it directly the way we map stars or gas. We infer its presence and its distribution only from its gravitational effects on things we can see, and from the way it shapes the structure of the universe on every scale, from individual galaxies to the largest observable structures. Every map of dark matter that exists is in a sense a negative image, a map drawn by the way ordinary matter moves in response to an invisible influence, the outline of a presence detected entirely by its consequences. What makes this so fascinating is that this method of inference, knowing something is there because of what it does to everything around it without ever seeing it directly, is not new in science. In the 19th century, astronomers inferred the existence of Neptune before they ever saw it, simply from the perturbations it produced in the orbit of Uranus. In the early 20th century, physicists inferred the existence of the neutrino from the energy missing in certain radioactive decays before any detector was sensitive enough to catch one. Dark matter follows this tradition, but on a vastly grander scale. Not a single planet or a single particle type inferred from a subtle anomaly, but the dominant component of all matter in the universe, inferred from the motions of billions of stars across hundreds of billions of galaxies. The first serious scientific evidence that the universe contains more matter than can be seen was gathered in the 1930s by a Swiss astronomer working in California named Fritz Zwicky, and it came from an unexpected direction: the way galaxies move within clusters. A galaxy cluster is a collection of hundreds or thousands of galaxies bound together by their mutual gravity, the largest gravitationally bound structures in the universe, separated from each other by millions of light years, but close enough on cosmic scales that their gravity holds them in orbit around the cluster's common center of mass. Zwicky was studying the Coma cluster, a rich concentration of galaxies about 320 million light-years from Earth, and he was measuring the velocities of individual galaxies within the cluster by observing the Doppler shifts of their light, the way the wavelength of light from an approaching galaxy is compressed to shorter, bluer wavelengths, and the light from a receding galaxy is stretched to longer, redder wavelengths. When he added up the masses of all the visible galaxies in the cluster and calculated how fast they should be moving under the gravity of that total mass, he found a serious discrepancy. The galaxies were moving far too fast. According to the visible mass, the cluster should not be able to hold itself together at all. The galaxies were moving with enough speed to escape the cluster's gravitational pull. If the only gravity available was the gravity of the visible matter. But the cluster was clearly there, clearly gravitationally bound, clearly not flying apart. Zwicky concluded that there must be additional, invisible mass holding the cluster together, far more than the visible galaxies could account for. He called it dunkel Materie, dark matter, and estimated that the cluster must contain many times more invisible matter than visible. The remarkable part is that Zwicky's conclusion was largely dismissed or ignored by the astronomical community for several decades. The tools to follow up his work were limited. The theoretical framework to make sense of the result was absent, and the idea of matter that could not be seen seemed speculative to the point of being unscientific to many of his contemporaries. He was, in retrospect, entirely correct, and his insight preceded the general acceptance of dark matter by nearly 40 years. A reminder that in science, being right too early can be almost as difficult as being wrong. He was, in retrospect, entirely correct, and his insight preceded the general acceptance of dark matter by nearly 40 years. A reminder that in science, being right too early can be almost as difficult as being wrong. Part of Zwicky's difficulty was temperamental. He was famously combative, and his colleagues found him difficult to work with, which may have colored their reception of his scientific ideas. Part was methodological. His calculation relied on estimates of galaxy distances and masses that were uncertain at the time, and critics could attribute the discrepancy to measurement error. And part was simply conceptual. The idea of matter that could not be seen was deeply counterintuitive in an era when matter meant visible matter, when the universe was thought to contain approximately what could be observed. The assumption that what we see is what there is runs very deep in human thinking, and science has had to fight against it repeatedly. In every domain where the invisible has turned out to be more important than the visible. In the case of dark matter, that fight took 4 decades and required not only better data, but a broader community of researchers, multiple independent lines of evidence, and a theoretical framework, the development of computational cosmology that could show how dark matter's presence would leave observable signatures on every scale from individual galaxies to the cosmic web itself. Zwicky's letter to the scientific community sat in the archive for decades, largely unreferenced, until the rotation curve work of the 1970s provided the independent confirmation that finally shifted the consensus. The history of his idea is a particularly clear example of a recurring pattern in science. The initial evidence arrives, is contested or ignored, then accumulates from multiple directions until it becomes undeniable, and the person who first saw it rarely lives to see the moment of acceptance as uncomplicated triumph. Zwicky's dark matter, specifically, passed through several phases of credibility over the decades. After the initial dismissal of his 1933 result, the concept resurfaced occasionally in the literature, but without the sustained attention it would eventually receive. The astronomer Sinclair Smith independently found a similar mass discrepancy in the Virgo cluster in 1936, reaching the same conclusion Zwicky had and receiving a similarly limited response. The problem of missing mass was real and documented, but the astronomical community had no framework for understanding it and no strong motivation to pursue it when so many other pressing questions occupied the field. It was only as the tools of radio astronomy and photographic spectroscopy improved in the 1950s and 1960s that the systematic measurement of galaxy rotation curves became possible, and only with those curves that the evidence became impossible to attribute to observational uncertainty. Zwicky did not live to see the full vindication of his 1933 paper. He died in 1974, 1 year before the publication of the rotation curve work that would transform dark matter from an anomaly into a scientific consensus. The pattern of his story, early insight, long dismissal, eventual confirmation by independent means, is not unusual in the history of science, but it is particularly stark in the case of dark matter, because the evidence he had was, in retrospect, entirely sufficient to support his conclusion. The discrepancy he found was not marginal or ambiguous. It was enormous, a factor of several hundred in missing mass, a discrepancy that shouted rather than whispered, but shouting into the void of an unprepared scientific community produces the same silence as whispering. The evidence that truly persuaded the astronomical community that dark matter is real came in the 1960s and 1970s from observations of the rotation of individual galaxies, and much of the most compelling early work was done by an American astronomer named Vera Rubin, working with her collaborator, Kent Ford. Rubin was measuring the velocities of stars and gas at different distances from the centers of spiral galaxies, using the Doppler shift of their spectral lines to determine how fast each part of the galaxy is rotating. The expectation, based on the distribution of visible matter in a typical spiral galaxy, was clear and seemed reasonable. Most of the mass of a galaxy is concentrated in the bright central bulge, which contains the majority of the stars, and the spiral arms extending outward contain progressively less mass. If most of the mass is at the center, then objects orbiting at larger distances should move more slowly, in the same way that the outer planets of our solar system move more slowly than the inner ones, because they are farther from the mass-concentrated sun. This relationship, called Keplerian rotation, after the astronomer who first described the orbital mechanics of the solar system, was expected to show up clearly in galactic rotation curves, graphs showing the orbital velocity of material against its distance from the galactic center. What Rubin and Ford found was entirely different. As they measured galaxies one after another, the rotation curves were flat. The orbital velocity of stars and gas did not fall off with distance from the center. It stayed roughly constant all the way out to the very edges of the observable disk of each galaxy and beyond. Stars in the outermost reaches of a spiral galaxy were moving just as fast as stars much closer to the center. By the laws of gravity and orbital mechanics, this is only possible if there is mass distributed throughout the galaxy, not just concentrated at the center, mass extending far beyond the visible stellar disk and providing enough gravitational pull to keep the outer stars moving at the velocities observed. The mass required to flatten the rotation curves was far greater than the visible mass of the galaxy. The flat rotation curves implied that each galaxy is embedded in a vast extended halo of invisible matter, a dark matter halo that dwarfs the visible stellar disk in both mass and physical extent. What makes this so compelling is the universality of the finding. Rubin and her collaborators measured dozens of galaxies of different types and sizes, and the flat rotation curves showed up everywhere. This was not a peculiarity of one unusual galaxy or one anomalous measurement. It was a systematic feature of galaxies in general, a property of the universe itself, and it demanded, unambiguously, that most of the matter in the universe is not the matter we can see, and it demanded, unambiguously, that most of the matter in the universe is not the matter we can see. Rubin's work was significant not only for its scientific content, but for its meticulous methodology and its systematic scope. She did not measure one galaxy and argue from a single case. She and her collaborators measured dozens of galaxies, different types, different sizes, different environments, and the flat rotation curves appeared everywhere. The consistency of the result across such a diverse sample was what made it impossible to attribute to a peculiarity of any individual galaxy. Each new galaxy measured was another datum, another confirmation, another weight added to the scales. Rubin was also a significant figure in the history of women in science, having been the first woman permitted to use the Palomar Observatory and having navigated a career in which she was repeatedly underestimated. She was nominated for the Nobel Prize in Physics multiple times, and many scientists considered her omission from the prize before her death in 2016 a significant oversight. Her contributions to cosmology are now considered foundational, and the dark matter problem she helped bring to the center of astrophysics has been one of the defining questions of the field ever since. The flat rotation curve is the result she is most associated with, a simple graph with distance on one axis and velocity on the other, and a line that refuses to fall when everything in our understanding of gravity says it should. That stubbornly flat line, repeated galaxy after galaxy, is one of the most eloquent data signatures in the history of astronomy, pointing with quiet insistence at the existence of something we do not yet understand. The flat rotation curve has another property that deserves attention. It is a prediction, not merely an observation. Once the dark matter halo is postulated, its properties can be inferred from the rotation curve, and those inferred properties can be checked against predictions from cosmological simulations of how dark matter halos form and evolve. The agreement between the inferred halo properties and the simulated halo properties is, across thousands of galaxies studied in the decades since Rubin's initial work, remarkably consistent. The dark matter halo is not just an ad hoc addition to make a graph fit. It is an entity with specific predicted properties, a specific density profile, a specific mass-to-light ratio, a specific relationship to the visible galaxy it surrounds, and the observations bear out those predictions in detail. This predictive success is part of what gives the dark matter hypothesis its scientific solidity. It is not merely a description of what is observed, but a framework that makes specific, testable predictions about observations not yet made. At the time the framework was developed, and those predictions are confirmed. The wonder comes from the accumulation. Decades of rotation curves, thousands of galaxies, all pointing the same direction, all demanding the same invisible companion, all confirming that what Vera Rubin and Kent Ford saw in the early 1970s was not an anomaly, but a fundamental feature of the universe. One of the most visually dramatic pieces of evidence for dark matter comes from a cosmic collision observed halfway across the observable universe. a collision so illuminating in what it revealed that it is sometimes called the most direct evidence for dark matter yet obtained. The object is called the Bullet Cluster, and it consists of two galaxy clusters that passed through each other roughly 150 million years ago at a speed of approximately 2,000 kilometers per second, one of the fastest known collisions of galaxy clusters. When the two clusters collided, the galaxies themselves mostly passed through each other without incident, because the space between stars within galaxies is so vast that direct stellar collisions are extraordinarily rare. The hot gas that fills the space between the galaxies within each cluster, however, is spread continuously through the cluster volume, and when the two gas clouds met, they interacted, they collided, they slowed, they heated to hundreds of millions of degrees, and they ended up in the middle of the merged cluster, glowing brilliantly in X-ray wavelengths that can be detected by space-based X-ray telescopes. If all the mass of the clusters were in this hot gas, the X-ray glow would mark the location of most of the mass. But astronomers also mapped the distribution of mass in the Bullet Cluster by observing gravitational lensing, the way that mass curves space-time and bends the paths of light from background galaxies passing near the cluster. Gravitational lensing depends only on mass, not on whether that mass emits or absorbs light, and so it provides a direct map of where the mass actually is, regardless of whether it is visible. When the lensing maps were compared to the X-ray maps, the result was striking. The mass inferred from lensing was not concentrated where the X-ray gas was glowing, at the center of the collision where the ordinary gas had been slowed and piled up. The mass was offset from the gas, still located approximately where the two original clusters had been before the collision, as though most of the mass had passed through the collision without being slowed or scattered, continuing forward while the gas was left behind. The mass that passed through was the dark matter halos of each cluster, which, like the individual galaxies, barely interact with anything and sailed through the collision unimpeded. The gas, made of ordinary particles that interact strongly with each other, was stopped and left behind. The Bullet Cluster showed, in a single image that could be pointed to directly, the separation of visible matter from the dark matter it normally coincides with. The wonder comes from the fact that this is not an inference drawn from statistics or from subtle theoretical arguments. It is visible in the data, a gap between where the light is and where the mass is, pointing with unmistakable clarity to the existence of a substance that responds to gravity, but not to any other force that acts on the matter we are made of. Pointing with unmistakable clarity to the existence of a substance that responds to gravity, but not to any other force that acts on the matter we are made of. The Bullet Cluster result was also significant because it placed tight constraints on how dark matter interacts with itself. If dark matter particles scattered strongly off each other, the dark matter halos of the two clusters would have been slowed by their mutual collision, in the same way the gas was slowed, and would not have passed through each other cleanly. The fact that the dark matter appears to have passed through almost unimpeded means that dark matter's self-interaction, cross-section, the measure of how strongly it scatters off itself, is very small, setting an upper limit on what self-interacting dark matter models can predict. Subsequent studies of other merging clusters have refined these constraints, and the picture that emerges is consistent. Dark matter is very close to collisionless, interacting with itself and with ordinary matter almost not at all, except through gravity. This constraint has shaped theorists' thinking about what dark matter can be, ruling out variants that interact too strongly and focusing attention on candidates whose self-interaction falls within the observationally allowed range. The bullet cluster has therefore been important, not just as evidence for dark matter, but as a precision measurement of dark matter's properties, contributing to the gradual narrowing of the field of candidates that is one of the primary ways science makes progress when direct detection remains elusive. Science makes progress not only by discovering what things are, but also by carefully ruling out what they are not. And in the case of dark matter, decades of meticulous work have narrowed the field of candidates by eliminating an impressive list of possibilities. One of the earliest and most reasonable suggestions was that dark matter might be ordinary matter in forms that are simply very difficult to see. Dim stars, too faint to be detected at large distances, black holes, neutron stars, brown dwarfs, or rogue planets drifting through interstellar space without any star to illuminate them. These objects, collectively called MACOs, which stands for Massive Compact Halo Objects, would all be made of ordinary atomic matter, just arranged in forms that emit little or no light. If the dark matter halos of galaxies were filled with MACOs, the gravitational lensing they produced as they drifted in front of background stars would occasionally produce a characteristic brightening event as the MACO's gravity bent and focused the background star's light toward Earth. Astronomers searched for these micro-lensing events extensively through the 1990s and 2000s, monitoring millions of stars in the Milky Way and in nearby galaxies, looking for the characteristic symmetric brightening and fading that a passing MACO would produce. They found some, but far too few to account for the dark matter. MACOs can explain at most a small fraction of the missing mass. Another candidate, suggested soon after the detection of the cosmic microwave background, was that dark matter might be made of ordinary baryonic matter in forms not yet accounted for, warm intergalactic gas, or cool clouds of hydrogen, too diffuse to have been detected. But measurements of the cosmic microwave background and of the abundances of light elements produced in the first minutes after the Big Bang constrain very precisely how much ordinary baryonic matter the universe can contain, and the number is firmly too small to explain the full dark matter budget. The universe simply does not have enough ordinary atomic matter to account for the dark matter halos of galaxies. Whatever dark matter is, it is not made of protons and neutrons. It is something else, something that was produced in the early universe in vast quantities, but that interacts with ordinary matter and with light through gravity alone, a substance that the standard model of particle physics, our best current framework for describing the elementary particles and their interactions, does not contain. The fascinating part is that this exclusion is itself profound. Dark matter's existence is, among other things, the clearest evidence we have that the standard model, for all its extraordinary success in describing the particles we can detect, is incomplete. Something is missing from our deepest description of the contents of the universe, and dark matter is the clearest signal of that gap. The standard model has been tested with extraordinary precision at particle accelerators and in precision measurements of atomic properties, and it has passed every test to which it has been subjected. It correctly predicts the magnetic moment of the electron to 11 decimal places, a feat of agreement between theory and experiment that has no parallel in any other area of science. It correctly predicted the existence and properties of the W and Z bosons before they were detected, the top quark before it was found, and the Higgs boson, the particle associated with the mechanism that gives other particles their masses, before the Large Hadron Collider at CERN confirmed its existence in 2012. The Standard Model is arguably the most precisely confirmed scientific theory in human history, a framework so successful that it has survived every experimental test for more than 50 years without a single confirmed failure. And yet, it contains no dark matter candidate. It describes in exquisite detail the 5% of the universe that we can directly observe, and it is completely silent on the remaining 27%. This silence is not a small deficiency in an otherwise complete framework. It is the largest outstanding gap between theory and observation in all of physics, a gap that tells us something fundamental. The physics we have discovered so far, remarkable as it is not the whole of physics. There is a sector of physical law, perhaps a rich and complex sector, with its own particles and forces and interactions, that we have not yet accessed with any experiment, a hidden sector that touches our world only through the one force that cannot be screened or shielded: gravity. The leading theoretical candidate for dark matter for several decades has been a class of hypothetical particles called WIMPs, which stands for weakly interacting massive particles. The name describes their key properties precisely. They interact weakly through what physicists call the weak nuclear force, the same fundamental force responsible for certain types of radioactive decay. And they are massive, having a mass perhaps 100 times that of a proton, though estimates span a wide range. WIMPs are appealing as dark matter candidates for a reason that physicists find almost irresistible, a coincidence so numerically precise that it has been given its own name, the WIMP miracle. The argument goes like this. In the hot, dense conditions of the very early universe, in the first fractions of a second after the Big Bang, particles of all kinds were being created and destroyed in rapid equilibrium. As the universe expanded and cooled, each type of particle reached a point where the temperature fell too low for it to be produced, and its interactions became too rare to keep it in equilibrium with the rest of the plasma. At that point, the remaining particles of that type froze out, settling into a stable population that persisted to the present day. The abundance of a given particle species that survives this freeze-out depends on how strongly it interacts with other particles. Particles that interact more strongly annihilate more efficiently and leave behind fewer survivors, while particles that interact more weakly annihilate less efficiently and leave behind more. If you take a hypothetical particle with a mass and interaction strength that are entirely independently motivated by particle physics, theories developed for completely unrelated reasons, specifically the theories that attempt to solve problems in the standard model of particle physics, such as supersymmetry, and you calculate how many such particles would survive to the present day. You get a number that matches the observed dark matter density of the universe to within a factor of a few. A particle invented for reasons having nothing to do with cosmology produces, through a calculation having nothing to do with galaxy rotation curves, approximately the right abundance to be the dark matter. This coincidence, the WIMP miracle, persuaded generations of physicists that WIMPs were not merely plausible dark matter candidates, but probably the correct ones. The deeper fascination is that this near certainty has been tested relentlessly, with increasingly sensitive detectors buried deep underground to shield them from cosmic ray background noise. And despite decades of searching, no WIMP has ever been conclusively detected. The detectors have grown more sensitive by many orders of magnitude, ruling out progressively larger regions of WIMP parameter space, and the silence has continued. WIMPs are not ruled out, but the confidence that they are the answer has been tempered by the long and so far unsuccessful search, and the field has broadened significantly to consider other candidates. The silence of the detectors has also inspired a productive reassessment of the theoretical landscape. Physicists who spent careers building models of WIMPs have branched out, considering lighter particles, heavier particles, particles that interact through forces not included in the standard model, particles produced not by thermal freeze-out, but by other mechanisms in the early universe. The field of dark matter theory is now far broader and more diverse than it was 2 decades ago, which is, in the long run, a healthy response to persistent null results. Science advances through the closing of doors as well as through the opening of them, and each WIMP exclusion region is a door closed, a patch of theoretical space eliminated, a constraint that future theories must respect. The WIMP miracle remains beautiful, and WIMPs remain viable candidates, but the certainty has given way to a more open and exploratory attitude that has enriched the field considerably. The search for dark matter particles directly, by attempting to catch one in the act of colliding with an ordinary atomic nucleus, is one of the most demanding experimental endeavors in the history of science. The challenges are extreme and layered. Dark matter particles, if they are WIMPs or anything similar, are expected to pass through matter almost without interaction, much like neutrinos, which are so weakly interacting that they pass through the entire Earth with only an infinitesimal chance of hitting anything. On very rare occasions, however, a dark matter particle might strike an atomic nucleus and cause it to recoil slightly, transferring a small amount of energy that a sufficiently sensitive detector could measure. The signal expected from such a collision is extraordinarily faint, a nucleus recoiling with an energy of a few to a few tens of kilo-electron-volts, a tiny fraction of the energy deposited by even the lowest energy ordinary radiation. To detect this signal requires building detectors of extraordinary sensitivity and placing them in environments of extraordinary quiet. The experiments that have led this search are located deep underground, in mines and tunnels far below the surface, because the rock above provides shielding against the constant rain of cosmic ray particles that would otherwise produce millions of false signals for every genuine dark matter interaction. The Lux Zeppelin detector in the Homestake mine in South Dakota, for example, operates nearly 1.5 miles underground in a tank containing 10 tons of liquid xenon, maintained at extremely low temperatures. When a particle interacts with a xenon nucleus, the interaction produces both a flash of ultraviolet light and a pulse of electrons that drift upward through the liquid under an applied electric field and produce a second, larger flash of light when they reach the surface of the liquid. The combination of the two signals allows the detector to determine the position of the interaction in 3 dimensions and to distinguish nuclear recoils, the signature of dark matter from the electronic recoils produced by ordinary radioactive decay and other backgrounds. These detectors have reached a sensitivity where they can detect a single radioactive decay event from trace amounts of uranium or thorium in their components, where the number of background events must be counted in single digits per year, and where the materials used in construction must be selected and purified to a degree that would seem absurd outside this specific scientific context. And yet, despite this extraordinary sensitivity, no confirmed dark matter detection has been announced. The detectors have set progressively tighter limits on how often dark matter particles can interact with ordinary matter and how massive they must be, ruling out vast swaths of theoretical parameter space. But the particle itself has not been found. This is one of the reasons the search is so scientifically valuable, even in its silence. The exclusion regions established by these experiments are themselves profound constraints on the nature of dark matter, eliminating candidates and refining theories in ways that will eventually, scientists believe, lead to the answer. There is also a complementary approach to dark matter detection that has been growing in sophistication. Indirect detection, the search for signals produced when dark matter particles annihilate or decay in regions of high dark matter density. If dark matter is a WIMP, then two WIMPs meeting in the dense center of a galaxy or a dark matter halo can annihilate, producing ordinary particles including photons, neutrinos, and electron-positron pairs. Space-based gamma-ray telescopes, particularly the Fermi Large Area Telescope, have been searching for the excess gamma-ray emission that such annihilations would produce at the centers of galaxies and in dwarf satellite galaxies of the Milky Way, which are among the most dark matter-dominated objects known. An excess of gamma rays from the center of the Milky Way was detected and sparked considerable excitement, but subsequent analysis has debated whether the excess is consistent with dark matter annihilation, or whether it is more simply explained by a population of unresolved millisecond pulsars, rapidly spinning neutron star remnants that produce gamma rays through ordinary astrophysical processes. The debate is ongoing, unresolved, and illustrative of the difficulty of indirect detection. The signals expected from dark matter annihilation look very similar to signals that ordinary astrophysics can also produce, and distinguishing them requires a level of precision in modeling the astrophysical background that is not yet fully achieved. While WIMPs have historically dominated the theoretical imagination of dark matter physics, another candidate has been gaining ground steadily, both in theoretical respectability and in the ambition and sophistication of the experiments designed to find it. The axion is a hypothetical particle that was not invented to solve the dark matter problem. It was invented in 1977 by the physicists Roberto Pecci and Helen Quinn to solve an entirely unrelated puzzle in particle physics, a puzzle called the strong CP problem. The strong nuclear force, which binds quarks together inside protons and neutrons, is described by a theory called quantum chromodynamics. The equations of quantum chromodynamics include a parameter that, for reasons unrelated to dark matter, would be expected to take a large value, and that large value would cause certain physical effects. Specifically, it would cause the neutron to have a measurable electric dipole moment, a slight separation of positive and negative charge within the particle, of a predictable size. Experiments measuring the electric dipole moment of the neutron have found it to be extraordinarily small, consistent with zero to extraordinary precision. The parameter that should make it large appears to be, for no obvious reason, essentially zero. Pecci and Quinn proposed a mechanism that would dynamically set this parameter to zero through the existence of a new symmetry and its associated particle, which physicist Frank Wilczek named the axion after a brand of laundry detergent because it cleaned up the problem. The axion, if it exists, would be produced in vast quantities in the early universe, would have an extremely small mass, far lighter than the electron, and would interact so weakly with ordinary matter as to be almost impossible to detect by conventional means. It would also, if produced in sufficient quantities, constitute a form of cold dark matter consistent with the large-scale structure of the universe. The WIMP miracle is a coincidence of abundance. The Axion solution is a coincidence of motivation. A particle invented to fix a problem in nuclear physics turns out, if it exists, to also be a viable dark matter candidate. Experiments searching for axions use a completely different approach from direct detection experiments. They attempt to convert axions into photons in the presence of a strong magnetic field, a process the equations of quantum chromodynamics permit with a small but non-zero probability. The ADMX experiment in the United States and the Haystack experiment have been scanning through axion mass ranges with increasing sensitivity, looking for the faint microwave photon signal that would indicate an axion has converted in their detector. The search is painstaking because the frequency of the photon produced depends on the axion mass, and the axion mass is not known from theory. The detectors must be tuned through a range of frequencies, spending enough time at each to accumulate a usable signal-to-noise ratio. It is, in its patience and its methodical progression, one of the most distinctive scientific searches ever conducted. A slow sweep through a space of possibilities, frequency by frequency, year by year, listening for a whisper. The Axion search is also benefiting from advances in quantum information science in ways that illustrate how progress in one area of physics can unexpectedly enable progress in another. Quantum sensing techniques, developed partly for quantum computing research, allow the construction of microwave detectors that operate at or near the quantum noise limit, meaning they are sensitive to the minimum possible level of noise allowed by the fundamental uncertainty principle. At this sensitivity, even the extraordinarily faint signal from axion to photon conversion in a strong magnetic field becomes detectable over a period of integration, accumulating signal while the quantum noise averages down. The use of squeezed states of light, in which the quantum uncertainty is redistributed from the measured quadrature to an unmeasured one, has further improved the sensitivity of recent experiments, and future axion searches incorporating quantum-enhanced receivers may be able to scan the favored axion mass range within years rather than decades. The convergence of cosmological motivation and quantum technology is one of the more remarkable features of the current moment in physics. A particle proposed to solve a problem in nuclear physics, whose existence would also explain the dark matter, being searched for using techniques developed for quantum computing. The universe's hidden substance and humanity's most advanced information technology, brought together in a laboratory in the quiet pursuit of an answer. If you could somehow step outside the universe and view it from a vantage point of sufficient distance, you would see not a uniform fog of galaxies distributed evenly through space, but a vast and intricate cosmic web, sheets and filaments of galaxies stretching for hundreds of millions of light years, surrounding enormous, nearly empty voids, all intersecting at dense nodes where the largest galaxy clusters congregate. This large-scale structure of the universe, the cosmic web, is one of the most striking features of the observable cosmos, and it is made almost entirely of dark matter. The ordinary matter, the atoms and molecules and stars and gas that we can observe, traces the dark matter distribution in the same way that cream traces the currents in a cup of coffee when you pour it in. The cream is not causing the currents. It is simply following them. The galaxies are not causing the large-scale structure of the universe. They are following the distribution of dark matter, condensing wherever dark matter has already gathered. The formation of this cosmic web began in the very early universe, before the first stars existed, from tiny quantum fluctuations in the density of matter that were present at the moment of the Big Bang and were inflated to cosmic scales during the period of rapid expansion called inflation. Dark matter, unlike ordinary matter at that epoch, was not prevented from clumping by the pressure of radiation because it does not interact with radiation. It began to collapse under gravity immediately, forming the first dark matter structures, while the ordinary matter was still a smoothly distributed plasma. Over hundreds of millions of years, these dark matter structures grew, merging with each other in a bottom-up process called hierarchical structure formation. Small dark matter, halos, formed first, then merged to form larger ones, which merged to form larger ones still. The largest galaxy clusters we see today are the most massive dark matter halos in existence, built by billions of years of merging and accretion. Only after the dark matter halos formed did the ordinary matter follow, flowing into the gravitational wells carved by the dark matter, and eventually condensing into the stars and galaxies we can observe. What makes this so captivating is that simulations of the universe, beginning with only the known physics of dark matter and ordinary matter, with initial conditions set by the quantum fluctuations observed in the cosmic microwave background, reproduce the large-scale structure of the universe with remarkable fidelity. The cosmic web seen in galaxy surveys matches the cosmic web predicted by dark matter simulations in its statistical properties, its filament lengths, its void sizes, its cluster mass distribution. Dark matter is not just an add-on to make individual galaxy rotation curves work. It is the architect of the entire large-scale structure of reality. The simulations that demonstrate this, known as N-body simulations, begin with an initial distribution of dark matter particles set by the conditions of the early universe, inferred from the cosmic microwave background, and then evolve the system forward in time under the influence of gravity alone, allowing the dark matter to cluster and merge and form halos over 13 billion years of simulated cosmic evolution. The resulting distributions of dark matter halos, when compared to galaxy surveys, show remarkable agreement in their statistical properties. The number of halos of a given mass per unit volume, the clustering of halos, the shapes of the filaments connecting them, all match the observations with a fidelity that would be difficult to explain if dark matter were not the dominant gravitational ingredient. Adding ordinary matter to these simulations, allowing it to fall into dark matter halos and form stars and galaxies according to known physics, produces simulated universes that increasingly resemble the actual universe in their galaxy populations, their star formation rates, their galactic morphologies, and their large-scale structure. The agreement is not perfect. It is the imperfections, the tensions at small scales, the missing satellite problem, the cusp core problem, that are driving the next generation of theoretical work. But the broad picture is robust, and it is built on a foundation of dark matter. The universe we see, with all its structure and all its beauty, is, in the most fundamental gravitational sense, a dark matter universe with a thin, luminous coating. One of the most powerful and independent lines of evidence for dark matter comes not from the present-day universe, but from a snapshot of the universe when it was only about 380,000 years old. At that moment, which cosmologists call recombination, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before recombination, The universe was a dense, hot plasma in which photons were constantly scattered by free electrons, unable to travel freely in any direction. After recombination, the newly formed neutral atoms were transparent to photons, and the photons that existed at that moment streamed freely outward in all directions, cooling as the universe expanded and persisting to the present day as the cosmic microwave background radiation, a faint glow of microwave radiation filling every direction in the sky with extraordinary uniformity. The cosmic microwave background is not perfectly uniform, however. It has tiny temperature variations, fluctuations at the level of roughly 1 part in 100,000, that trace the pattern of density fluctuations in the early universe at the moment of recombination. These fluctuations are the seeds from which all cosmic structure grew. The pattern of these fluctuations, measured with extraordinary precision by satellites including COBE, WMAP, and Planck, contains a wealth of information about the composition of the universe, encoded in a specific pattern of peaks and troughs called the acoustic power spectrum. Before recombination, the ordinary matter in the universe was locked in a tightly coupled plasma with the photons, and this plasma underwent oscillations, alternately compressing and expanding under the competing effects of gravity and radiation pressure, producing a characteristic pattern of acoustic waves frozen into the cosmic microwave background at the moment of recombination. Dark matter, which does not interact with photons, was not part of this coupled plasma. It clumped under gravity independently of the photon baryon fluid, and its gravitational influence affected the pattern of oscillations in a precise and calculable way. By fitting a model to the observed pattern of fluctuations in the cosmic microwave background, cosmologists can simultaneously determine the density of ordinary baryonic matter and the density of dark matter to high precision. The current best measurements find that ordinary matter makes up about 4.9% of the total energy density of the universe, while dark matter makes up about 26.8%. These measurements are made by a completely different method from galaxy rotation curves, gravitational lensing, or cluster dynamics, and they agree with all of those other lines of evidence, confirming that the dark matter abundance is not an artifact of any particular observational technique, but a real property of the universe. The fascinating part is that the cosmic microwave background was produced when the universe was less than 1/1,000,000th of its current age, and yet the dark matter that shaped its fluctuations is the same dark matter that shapes galaxy rotation curves today. The invisible substance has been constant and ubiquitous throughout nearly all of cosmic history. The precision of cosmological parameter measurements from the cosmic microwave background has also provided a strong consistency test of the dark matter picture. If dark matter is a particle species produced in the early universe, then its properties, including its mass, its interaction strength with ordinary matter, and its abundance, must be consistent not only with the large-scale structure of the present universe, but with the physics of the early universe as encoded in the cosmic microwave background. Models in which dark matter is too light, moving too fast in the early universe, are constrained by the fact that fast-moving dark matter would erase small-scale density fluctuations, producing a universe with less small-scale structure than is observed. This rules out neutrinos as the primary dark matter, since neutrinos are too light and move too fast. Models in which dark matter interacts with ordinary matter or with photons in the early universe are constrained by the detailed shape of the acoustic peaks, which would be affected by any coupling between the dark sector and the photon baryon fluid. The acoustic peaks, as measured by Planck, are entirely consistent with dark matter that does not interact with the photon-baryon plasma. Dark matter that is gravitationally present without being coupled, shaping the peaks from the outside, as it were, without leaving any signature of direct coupling inside the oscillating fluid. This consistency is itself a powerful constraint. Dark matter must be not just dark to visible light, but dark to the entire photon-baryon plasma of the early universe, interacting with none of it directly, influencing everything through gravity alone. The dark matter is not only found in distant galaxies and galaxy clusters, detectable only by its aggregate effect on millions of stars seen from hundreds of millions of light years away. It is here, surrounding the Milky Way, threading through the solar system, passing through the room you are resting in right now. The Milky Way is embedded in a dark matter halo that extends far beyond the visible disk of the galaxy, far beyond the most distant stars in the outer halo, far beyond even the Magellanic Clouds, the two small satellite galaxies that orbit the Milky Way. The dark matter halo of our galaxy is estimated to extend to perhaps 1 million light-years from the galactic center, dwarfing the visible disk, which spans only about 100,000 light-years. The total mass of the Milky Way's dark matter halo is estimated at roughly 1 to 2 trillion solar masses, far more than the mass of all the visible stars, gas, and dust in the galaxy combined, which amounts to only a few 100 billion solar masses. The dark matter halo is not uniform. It is densest at the center and falls off in density with increasing distance, following a profile that is predicted by simulations of dark matter, halo formation, and broadly confirmed by observations of stellar kinematics and gravitational lensing in other galaxies. Within the solar system, the local density of dark matter is estimated to be roughly a proton mass worth of dark matter per cubic centimeter, which sounds small, but amounts to about 300 million dark matter particle masses in every cubic meter if WIMPs are the dark matter, or an incomprehensible number of axions if axions are the answer. Dark matter particles are passing through your body right now, many thousands per second if they are WIMP mass particles, at speeds of around 230 kilometers per second, the typical speed of dark matter particles relative to the Sun in the Milky Way's halo. They pass through you without depositing any energy, without triggering any chemical reaction, without leaving any trace of their passage, exactly as they pass through the rock of a mountain or the iron of the Earth's core. You are, at this moment, a permeable membrane in a river of dark matter that has been flowing through this region of the galaxy since before the solar system formed, and you feel nothing, and nothing feels you, and the river flows on. There is an experiment in this fact. If you could make a detector sensitive enough to catch even one dark matter particle in the act of scattering off an ordinary nucleus, the rate of detections would tell you about the density and speed distribution of dark matter in the solar neighborhood, providing a direct measurement of our local dark matter environment with the same kind of specificity that a weather station measures the local wind. Every direct detection experiment is, at one level, measuring a property of the Milky Way's dark matter halo at the specific location of the detector. The results so far are upper limits, telling us how infrequent such collisions must be. But a positive detection would be extraordinarily informative. It would not just confirm dark matter's existence, but would reveal, through the energy spectrum and directionality of the recoil events, the local velocity distribution of dark matter particles, mapping the river that flows through us with a precision that no current technique can match. The Earth's motion around the Sun would produce an annual modulation in the detected signal, with more dark matter particles appearing to come from the direction the Earth is moving toward in summer, and fewer from that direction in winter, creating a seasonal rhythm in the detection rate that would serve as an unmistakable signature of dark matter from the galactic halo rather than any terrestrial or solar background. The Dama/Libra experiment has reported detecting exactly this kind of annual modulation for more than 2 decades. But the dark matter interpretation is strongly disputed because other experiments with greater sensitivity and different target materials have not seen the corresponding signal. The mystery within the mystery persists. Not every scientist who examined the anomalous galaxy rotation curves and the missing mass of galaxy clusters concluded that there must be new, undiscovered matter. Some asked instead whether the anomalies might indicate that our understanding of gravity is incomplete, that the equations governing gravity at very low accelerations or very large scales might need modification. The most developed and historically significant of these alternative proposals is modified Newtonian dynamics, usually called MOND, proposed by the Israeli physicist Mordechai Milgram in 1983. Milgram noticed that the flat rotation curves of galaxies appear not at a particular distance from the galactic center, but at a particular value of gravitational acceleration. Below a critical acceleration, roughly 100 billionth of a meter per second squared, which is extraordinarily feeble by everyday standards, the effective gravitational force seems to fall off more slowly than Newton's law predicts, producing flat rotation curves. Milgram proposed that below this critical acceleration, gravity simply behaves differently from the Newtonian prediction, in a way that produces flat rotation curves without requiring dark matter. MOND has had genuine successes. It predicts the rotation curves of individual galaxies with remarkable accuracy, particularly for low surface brightness galaxies, where dark matter models require more fine-tuning. There is a specific empirical relationship between the distribution of ordinary visible matter in a galaxy and its rotation curve, called the baryonic Tully-Fisher relation, and its extension, the radial acceleration relation, that MOND predicts naturally, and that dark matter models must work to reproduce. These successes kept the theory alive and serious for decades, despite the resistance of much of the mainstream cosmological community. But MOND has also encountered obstacles that have proven very difficult to overcome. It does not naturally produce the large-scale structure of the universe, the cosmic web, without substantial additional assumptions. It does not explain the acoustic peaks of the cosmic microwave background without requiring something that behaves very much like dark matter, sometimes called dark matter in a MOND framework, which rather undermines the original motivation for avoiding dark matter. And the bullet cluster, with its clear separation between the location of the mass and the location of the gas, is extremely difficult to explain in any framework that does not invoke a non-baryonic, collisionless substance. The state of the field is that dark matter remains the overwhelmingly favored explanation among working cosmologists and particle physicists, not because alternative theories are impossible, but because dark matter explains more evidence with fewer additional assumptions and without running into the specific contradictions that alternative gravity theories face. The deeper fascination is that even in its dominance, the dark matter paradigm continues to face puzzles and tensions at smaller scales, and the conversation between evidence and theory remains genuinely open. The small-scale tensions in the cold dark matter picture are taken seriously precisely because they are quantitative and specific enough to test. The cusp core problem involves the density profiles of dwarf galaxies, which can be measured through stellar kinematics and through the rotation of any gas present in these systems. The too big to fail problem involves the number and internal properties of the satellite galaxies of the Milky Way, which can be measured by direct observation of those satellites in increasingly sensitive sky surveys. Future surveys, including the Legacy Survey of Space and Time, planned for the Rubin Observatory, will discover thousands of new satellite galaxies of the Milky Way and nearby galaxies, dramatically improving the statistics available to test the predictions of dark matter models. If the discrepancies remain after accounting for the effects of ordinary matter physics, they will provide the strongest available evidence that dark matter is not as simple as the standard cold, collisionless picture assumes. If they disappear when realistic models of star formation and supernova feedback are included, that result too will be informative, demonstrating that the physics of ordinary matter in dwarf galaxies is more dramatic than previously appreciated. Either outcome advances understanding, and the conversation between the predictions of theory and the accumulating data of observation is one of the most active and productive in modern astrophysics. Among the more exotic candidates for dark matter that have attracted renewed interest in recent years is the possibility that dark matter is not a new type of elementary particle at all, but instead consists of black holes formed in the very early universe, before any stars existed. These hypothetical objects are called primordial black holes, and they differ fundamentally from the stellar mass black holes produced by the deaths of massive stars or the supermassive black holes at galactic centers. Primordial black holes would have formed from density fluctuations in the very early universe, in the first fractions of a second after the Big Bang, when the cosmos was so dense that regions slightly overdense compared to their surroundings could collapse directly to form black holes before any stars or galaxies existed. If the initial density fluctuations of the early universe had the right properties, vast numbers of primordial black holes could have formed across a wide range of masses, from objects lighter than an asteroid to objects far heavier than the Sun. The interest in primordial black holes as dark matter candidates was reignited significantly by the first LIGO detections of gravitational waves from merging black holes in 2015 and 2016. The black holes detected in those first events had masses of around 30 solar masses, which is somewhat larger than most models of stellar evolution predict for black holes formed from the collapse of massive stars. The possibility that these were primordial black holes, relics of the very early universe, prompted a new wave of theoretical and observational work. The allowed mass range for primordial black holes to constitute all the dark matter has been significantly constrained by observations. Very light primordial black holes have been ruled out because they would have evaporated via Hawking radiation over cosmic time and would not survive to the present. Primordial black holes in certain intermediate mass ranges are constrained by microlensing surveys. But windows remain, particularly for primordial black holes, in the mass range of a fraction of the mass of the Moon to a few tens of solar masses. What makes this candidate so captivating is its conceptual elegance. If primordial black holes are the dark matter, then dark matter is not a new particle requiring new physics beyond the standard model. It is gravitational, made of the same kind of space-time curvature that ordinary black holes represent, but formed in the extreme conditions of the earliest moments of the universe's existence. The dark matter of the cosmos would be, in this scenario, a vast population of invisible gravitational objects formed in the first heartbeat of time, each one a small and permanent scar in the fabric of space-time, drifting silently through the galaxy, passing through everything, affecting nothing but the slow curvature of space around them. The primordial black hole scenario has a particular kind of philosophical appeal that has kept it alive in the scientific imagination, even as other candidates have attracted more attention. Unlike particle dark matter candidates, primordial black holes require no new fundamental particles, no new forces, no extension of the standard model of particle physics. They require only that the early universe had density fluctuations of sufficient amplitude in the right mass range, and they are produced entirely by known physics applied to extreme conditions. If they are the dark matter, then dark matter is not a new ingredient of nature, but a new initial condition, a consequence of the specific way the universe began, rather than of any undiscovered principle. This conceptual parsimony is attractive, though the physics required to produce primordial black holes in the necessary abundance does require specific and not yet confirmed properties of the primordial power spectrum of density fluctuations. Gravitational wave detectors are now sensitive enough to detect the stochastic background of gravitational waves produced by a population of binary primordial black holes, and the shape and amplitude of this background, if detected, would provide information about the mass distribution of primordial black holes and help determine whether they can account for the observed dark matter abundance. The next generation of space-based gravitational wave detectors, particularly LISA, will be sensitive to the frequency range where this background would be most prominent, making the primordial black hole hypothesis directly testable by a completely different method from the lensing and dynamical constraints that have defined the search so far. There is a beautiful and somewhat counterintuitive irony at the heart of dark matter's role in the universe. Dark matter, the substance that outweighs all the ordinary matter in the cosmos by a factor of roughly 5-1, was absolutely essential to making the universe we inhabit possible, and yet it did not participate in almost any of the specific processes that built the structures we can observe. Stars form when ordinary gas cools, collapses, and ignites nuclear fusion. Dark matter cannot cool because cooling requires radiating energy as photons, and dark matter does not interact with photons. Dark matter cannot collapse into dense objects for the same reason. The process of collapse requires the dissipation of energy, and dark matter has no way to shed energy and sink to the centers of its halos. Ordinary matter, by contrast, can radiate energy as it falls into gravitational wells, cool down, and eventually settle into the thin rotating disk of a galaxy where stars form, where planets orbit, where chemistry becomes possible. Dark matter simply orbits in the extended, spherically symmetric halo, unable to lose energy efficiently enough to collapse further, remaining in the diffuse configuration it settled into when the halo first formed. This means that despite being the dominant form of matter in the universe by mass, dark matter has never formed a star, never harbored a planet, never been part of any chemical reaction, never been involved in any process of complexity. All the richness of the universe, the planets and the biospheres, and the chemistry and the information processing systems that we call life, is built entirely from the 5% minority of matter, the ordinary baryonic component that can radiate and cool and clump and react. Dark matter provided the gravitational framework within which all of this was possible. Without dark matter, halos to seed the initial collapse of gas, the first stars would not have formed when they did, and the universe would be a very different, probably far emptier place. But dark matter itself never participated in the complexity it made possible. It is the scaffolding that the builders forgot, present everywhere, invisible in the finished structure, essential to the fact that any structure exists at all, but absent from every detail of the structure itself. That contrast is one of the reasons dark matter occupies such a distinctive place in the scientific imagination. It is both utterly fundamental and completely uninvolved in everything that makes the universe interesting. This paradox, that the most abundant form of matter is also the most inert, has shaped the way cosmologists think about the relationship between structure and complexity. The universe's complexity, its stars, its chemistry, its biology, is not a property of its dominant component. It is a property of the minority component, the thin, luminous veneer of ordinary matter that can cool and clump and react. Dark matter provides the gravitational architecture, but none of the content. The galaxy you live in is a dark matter halo first and a stellar system second. And if you removed all the stars and gas and dust, the dark matter halo would continue, orbiting, persisting, structurally intact, completely indifferent to the loss. The universe's complexity lives in the thin film of baryonic matter clinging to the inside of dark matter structures. And that film, for all its richness and variety, is cosmologically negligible in mass. What makes this so captivating is the question it raises. Is ordinary matter's capacity for complexity a fundamental property of its nature, or is it an accident of its specific interactions? Could a universe made entirely of dark matter give rise to anything analogous to complexity, to structure, to information processing? We do not know. Dark matter, by definition, cannot cool and collapse and build galaxies and planets and life. But whether some other mechanism, some other set of properties, could produce analogous richness in a universe made of different stuff is a question that touches on the deepest foundations of why the universe contains anything interesting at all. Dark matter theory, in its broad outlines, is extraordinarily successful at explaining the universe on large scales, the cosmic web, the growth of galaxy clusters, the acoustic peaks of the cosmic microwave background, the general properties of galaxy halos. All of these are reproduced with remarkable fidelity by simulations that include dark matter in its simplest, most vanilla form, particles that interact only via gravity and perhaps through a weak nuclear force. But as the simulations have grown more detailed and the observations have grown more precise, certain tensions have emerged at smaller scales in the properties of individual galaxies and their satellite systems that have generated active debate about whether the simple picture of dark matter is entirely correct. One of the most discussed is called the cusp core problem. Dark matter simulations consistently predict that dark matter halos should have a sharp density spike at their centers, a cusp where the density rises steeply toward the galactic center. But observations of the distribution of mass in small, dark matter-dominated dwarf galaxies, which are the best laboratories for testing dark matter predictions because ordinary matter is relatively minor in them, often suggest a flatter, more uniform density profile at the center, a core rather than a cusp. Another tension is called the too big to fail problem. Simulations of the Milky Way predict more large, dense satellite galaxies than are observed around the actual Milky Way, and the discrepancy is large enough that it is difficult to attribute to simple selection effects. These tensions are taken seriously by theorists, and they have generated two broad classes of response. The first class invokes the effects of ordinary matter. Even in a universe with cold dark matter, the energy injected by supernovae and by the radiation of newly formed stars can push dark matter out of galactic centers, flattening cusps into cores and suppressing the formation of satellite galaxies. The second class invokes modifications to the properties of dark matter itself. Perhaps dark matter particles can interact with each other, not just through gravity, allowing them to scatter and exchange energy within halos in ways that would smooth out density cusps. This class of models, called self-interacting dark matter, has gained traction because the bullet cluster and similar systems provide constraints on how strongly dark matter can self-interact. But those constraints still leave significant room for self-interaction that could resolve the small-scale tensions. The remarkable part is that these tensions, rather than being a crisis for dark matter, are a productive frontier. They are refining our understanding of the detailed properties of dark matter, pushing the theory from a rough sketch toward a precise portrait. The universe is offering clues about the nature of dark matter at the level of individual galaxies, and the challenge is to read those clues correctly. The tools available to read those clues are improving rapidly. Computational simulations of galaxy formation have advanced from the early N-body simulations that tracked only dark matter to hydrodynamical simulations that include ordinary matter, gas cooling, star formation, supernova feedback, and the effects of active galactic nuclei, all running simultaneously on some of the largest supercomputers in existence. Simulations like Illustris, Eagle, and Illustris TNG have produced simulated universes that, when compared statistically to observed galaxy populations, show remarkable agreement in many properties, while still exhibiting tensions in others. The small-scale tensions, the cusp core problem, and the too big to fail problem are being addressed in these simulations by increasingly realistic modeling of stellar feedback, and early results suggest that supernovae-driven outflows can indeed smooth dark matter cusps into cores in dwarf galaxies, potentially resolving the problem within the standard cold dark matter framework. But whether the resolution is complete, whether it extends to all affected systems, and whether it requires any modification of dark matter's properties beyond what standard cold dark matter predicts, remains an active area of debate. The outcome of this debate matters not just for cosmology, but for particle physics, because a determination that dark matter must be self-interacting, or warm, or otherwise non-standard, would provide crucial guidance for the next generation of laboratory experiments and accelerator searches, narrowing the vast space of possible candidates to the specific region where nature actually lives. Among the many dark matter candidates that theorists have proposed, the sterile neutrino occupies a distinctive position. It is not as exotic as some, not as well motivated as others, but it sits at an interesting intersection of particle physics and cosmology. And it has the unusual property of being detectable, in principle, by a method completely different from any used to search for WIMPs or axions. Ordinary neutrinos are familiar particles, produced in vast numbers by the Sun, by supernovae, by nuclear reactors, and by cosmic ray interactions in the atmosphere. They interact via the weak nuclear force and gravity, and they have tiny but non-zero masses, a fact established by observations of neutrino oscillation in the late 1990s. Sterile neutrinos are hypothetical cousins of ordinary neutrinos that interact only via gravity, having no weak nuclear force interaction at all, which makes them completely invisible to any detector that relies on weak interactions. They would be produced in the early universe through a mixing mechanism connecting them to ordinary neutrinos. and if their mass is in a particular range, perhaps a few kilo electron volts, they would have the right properties to constitute warm dark matter, a variation that differs from cold dark matter in that the particles were moving at relativistic speeds in the early universe, which would wash out small-scale structures and potentially resolve some of the small-scale tension problems discussed earlier. The exciting feature of sterile neutrinos is a specific decay channel. Occasionally, a sterile neutrino can decay into an ordinary neutrino and a photon, an X-ray photon, with an energy equal to half the sterile neutrino's mass. This decay would happen very rarely because the sterile neutrino is long-lived by design, but it would happen, and the result would be a faint but detectable line of X-ray emission at a specific energy coming from regions rich in dark matter. In 2014, two independent groups of astronomers announced the detection of an unexplained emission line at approximately 3.5 kilo electron volts in the X-ray spectra of galaxy clusters and the Andromeda galaxy. The line did not correspond to any known atomic transition, and its energy and distribution were consistent with the decay of a sterile neutrino with a mass of 7 kilo electron volts. The announcement generated enormous excitement and an immediate debate that has continued ever since. Subsequent analysis has found the line in some data sets and not others, with statistical significance that fluctuates as different telescopes and different targets are analyzed. The current status is genuinely uncertain. The line may be a real dark matter signal, or it may be a combination of unidentified or poorly modeled atomic transitions, or an instrumental artifact. The fascination lies in what it would mean if it is real. A detection of dark matter through its decay products, a photon arriving at a telescope with the specific energy predicted by a specific theoretical model, would not merely confirm dark matter's existence, but would tell us precisely what it is, beginning the era of dark matter, particle physics in earnest. The 3.5 kilo electron volt line controversy illustrates a broader methodological challenge in indirect dark matter searches. The difficulty of distinguishing a genuine new physical signal from an imperfect model of known astrophysical processes. X-ray astronomy is complex. Galaxy clusters contain hot gas with a rich spectrum of emission lines from many different atomic species, and the modeling of these lines requires precise knowledge of the temperature, density, and elemental composition of the gas at every point in the cluster. A signal at 3.5 kilo electron volts sits in a region of the spectrum populated by weak lines from sulfur and argon and chlorine ions. And whether those known lines can fully explain the observed emission, or whether a residual dark matter signal remains after their contributions are modeled, depends critically on the quality of the atomic data used in the analysis. The field awaits a new generation of X-ray satellites with much higher spectral resolution, particularly the X-ray Imaging and Spectroscopy Mission, XRISM, launched in 2023, which will be able to resolve individual X-ray emission lines with a precision many times better than its predecessors. With XRISM data, the question of whether the 3.5 kilo electron volt line is real and unaccounted for by known atomic transitions, or whether it dissolves into a combination of known lines once those lines are resolved individually, will receive a definitive answer. That answer, whether it is yes or no, will advance science. Confirmation would be a landmark discovery, and a clean null result would eliminate one of the most discussed dark matter candidates and redirect effort elsewhere. The search for dark matter is not standing still. It is expanding simultaneously along multiple fronts, with experiments of unprecedented sensitivity being built or planned at the present moment, each targeting a different candidate with a different technique, and collectively covering more of the space of theoretical possibilities than any previous generation of instruments. Underground direct detection experiments are scaling up dramatically. The next generation of these detectors, including Xenon, NT, LZ, and Panda X, use tens of tons of liquid xenon and will reach sensitivities that test the remaining viable parameter space for WIMP dark matter at masses between a few and a few thousand times the proton mass more thoroughly than any previous experiment. If WIMPs exist in this mass range and interact with ordinary matter at or above a theoretical floor set by coherent neutrino scattering, the irreducible background from ordinary solar and atmospheric neutrinos, these experiments will find them. Below that floor, the ordinary neutrino background becomes an indistinguishable mimicry of dark matter interactions, and new strategies will be needed. Axion experiments are also advancing rapidly. The quantum technology revolution has brought quantum sensors into the Axion search, with experiments using quantum-enhanced microwave receivers capable of reaching the sensitivity needed to test models of dark matter axions at the masses most favored by theory. The ADMX-G2 experiment and newer designs using quantum squeezing and quantum-limited amplifiers are scanning through axion masses with a throughput and sensitivity that would have seemed impossible a decade ago, and they are beginning to enter the theoretically motivated territory where axions most plausibly live. At particle accelerators, the Large Hadron Collider at CERN has searched for evidence of dark matter production in proton-proton collisions, looking for events in which two protons collide and produce a spray of ordinary particles together with missing energy and momentum, the signature of a dark matter particle being produced and escaping the detector undetected. The absence of such events has constrained dark matter models significantly, particularly those connected to supersymmetry. Future accelerators, potentially including a proposed circular collider with a circumference of approximately 100 kilometers, would extend this search to higher collision energies. In space, the Rubin Observatory in Chile will map the shapes of billions of galaxies with extraordinary precision, using weak gravitational lensing to produce the most detailed maps ever made of the distribution of dark matter throughout the observable universe, testing predictions of dark matter models at a level of statistical power that will either confirm the standard picture in exquisite detail or reveal tensions demanding new physics. The fascination lies in the convergence. All of these different approaches, built on different physical principles and targeting different candidates, are closing in simultaneously. The question of what dark matter is may be answered within the coming decades, or it may require yet another generation of instruments and ideas that we cannot fully anticipate from where we stand now. Either way, the search is one of the great intellectual adventures of this era. What is striking about the current era of dark matter science is the sheer diversity of approaches being pursued simultaneously, each grounded in different physics and sensitive to different mass ranges and different interaction types. This diversity is strategic. No single experiment can cover the full range of dark matter candidates, and a dark matter particle discovered by one type of experiment, but not others, would immediately reveal something about which forces it participates in and which it does not. The complementarity of different search strategies is not a weakness of the field, but one of its greatest strengths. If a signal appears in a direct detection experiment, It can be cross-checked against collider searches and against indirect detection observations. If a signal appears in the axion search, the specific mass and coupling strength can be checked against cosmological predictions for the abundance of axions produced in the early universe. If a primordial black hole signal appears in gravitational wave data, the mass distribution can be compared against microlensing constraints. The dark matter problem will not be solved by a single experiment in isolation. It will be solved by a network of experiments and observations, each contributing a piece of the picture, each constraining what the others must find, until the picture is complete enough to identify the candidate uniquely. That network is being built right now, instrument by instrument, result by result, with a collective ambition and a collective patience that are among the most admirable qualities of contemporary science. Now we slow a little more, and the facts become less about the technical and more about the vast. Dark matter has been present since the very beginning of time as we understand it, since the first moments after the Big Bang, since the universe was a fraction of a second old and already far too hot and dense for any planet or star or galaxy to exist. It emerged from those first moments as a sea of particles or objects moving at speeds dictated by their temperature and their mass, cooling and slowing as the universe expanded, beginning to cluster under gravity within the first few 100,000 years, forming the first small halos within the first billion years, building the scaffolding of the cosmic web that would eventually guide the formation of the first stars and galaxies. For more than 13 billion years, this invisible substance has been present everywhere in the universe, filling the halos of galaxies, threading through the voids between them, passing through stars without pausing, passing through planets without depositing any heat, passing through every living organism that has ever existed on Earth, from the first single-celled ancestors to the present, without leaving a single detectable trace. The Earth has orbited the Sun more than 4.5 billion times, and through every one of those orbits, the dark matter halo of the Milky Way has surrounded and permeated everything in the solar system without ever announcing itself. The dinosaurs lived and died in a river of dark matter. The first humans looked up at the sky, and the dark matter was there, threading through them. Every civilization in the history of humanity has been embedded in a flow of dark matter, and not one of them knew it. Not because they lacked curiosity, but because dark matter gives no signal by which it can be known except through the most precise and systematic science. We are the first generation of life, as far as we know, to have understood that it is there at all. The remarkable part is how recent this understanding is. The first evidence came in the 1930s, was consolidated in the 1970s, and the term dark matter entered the common scientific vocabulary only within living memory. For the entirety of human existence before a few decades ago, the dominant component of the matter in the universe was entirely unknown and completely undetected. What we see with all our instruments and all our observations is a thin, illuminated minority of what exists, and the invisible majority has been here all along, patient and ancient, and utterly indifferent to whether it is known. And yet, there is something almost companionable about that indifference. Dark matter does not withhold itself out of any intention or design. It is simply what it is, present in the same places as everything else, obeying the same gravitational law as everything else, and invisible not by choice, but by nature. Every galaxy that has ever formed, Every cluster of galaxies, every filament of the cosmic web was shaped by dark matter, acting with perfect consistency and without variation across 13 billion years of cosmic time. The dark matter halo surrounding a galaxy 10 billion light-years away, seen as it was 10 billion years ago, obeys the same gravitational physics as the dark matter halo surrounding the Milky Way today. There is a kind of profound consistency in that, a constancy that spans scales and epochs in a way that almost nothing else in the universe does. Stars change, galaxies evolve, the universe expands and cools. But dark matter halos simply grow by accretion and merging, following the same gravitational physics they have always followed, patient as mathematics itself. To know about dark matter is to know about a presence that has been part of the environment of everything that has ever existed, a silent partner in every physical process, present at the formation of the first stars, and at the formation of the sun, and at the formation of the earth, and at every moment of the 4 billion year history of life on this planet, noticed by none of it, shaping all of it. There is a particular kind of humility that dark matter science demands of us, a humility that goes deeper than the ordinary recognition that the universe is vast and we are small. The universe being large is something we can, in a sense, absorb. We can look at images of distant galaxies and feel the scale as a kind of awe. But dark matter asks something more specific. It asks us to accept that even the category of matter, the stuff of which the world is made, is not adequately described by everything we can touch and see and measure. The atoms and molecules and particles that constitute ordinary matter, the matter of physics textbooks and chemistry laboratories and living cells and starlight, are a minority, an outlier, a special case. We are made of the exception. We are assembled from the small and peculiar fraction of the universe's matter that has the unusual property of being able to cool and clump and react and organize into structures of increasing complexity. And because we are made of this exceptional stuff, everything we have ever directly observed is also made of this exceptional stuff. We built our entire understanding of physics, of the fundamental constituents of matter, from the study of this minority component, and we arrived at an extraordinarily detailed and successful framework, the standard model of particle physics, that describes with precision everything we have ever detected in a laboratory. And then we looked at the universe on large scales and discovered that the framework describes only 5% of it. The rest, the dominant majority, is something else entirely. Something that does not fit in the standard model. Something for which we have no fundamental description beyond its gravitational effects. Dark matter is, in this sense, the universe's most patient rebuke of human intellectual confidence. Every time we have convinced ourselves that we understood the basic structure of physical reality, the universe has offered a new and larger category of ignorance. Dark matter is the current frontier of that sequence. The deeper fascination is that this is not discouraging, but energizing. The existence of dark matter means the universe is larger and stranger and richer than the universe we can directly observe, and that the next layer of understanding, when it finally arrives, will reveal not just what dark matter is, but what its existence implies about the deeper structure of physical law. That revelation is out there, waiting in the data of experiments being run right now, in the mathematics of theories being worked out by physicists sitting at desks in the quiet hours. This mystery is also, in a particular way, a gift to science as a practice, as a human endeavor. The history of physics in the 20th century is sometimes told as a story of triumphant completion, the standard model accounting for nearly everything observable, quantum mechanics and general relativity providing the foundations of all physical law. But dark matter insists that the story is not complete, that the universe has not yet yielded its deepest secret, that the most fundamental question about the contents of nature, what is matter made of, remains open. This is not a failure. It is a reprieve, an assurance that the great questions are not yet exhausted, that there is still something profound to discover, that the work is not done. Generations of physicists in the coming decades will devote their careers to this question, building instruments and developing theories, and arguing over data with the same passion and precision that characterized the physicists who discovered quantum mechanics and general relativity. And one day, perhaps not so far in the future, one of them will see the signal, will recognize it for what it is, and will begin the process of telling the rest of the world what dark matter is. That moment, when it comes, will be one of the great moments in the history of human knowledge, a moment comparable to the discovery of the structure of DNA or the confirmation of gravitational waves, a moment when the most pervasive substance in the universe finally shows its face. There is something that deserves to be said about the state of not knowing, about the condition of being certain that something vast and important exists without yet knowing what it is. Dark matter has been in this condition for nearly a century, unambiguously real, evidenced from dozens of independent directions, absolutely central to our understanding of how the universe works, and fundamentally unknown in its nature. This is an unusual position for a scientific concept to be in for so long. Most of the other great mysteries of 20th century physics, the nature of the atomic nucleus, the mechanism of radioactivity, the origin of the cosmic microwave background, the expansion of the universe, were resolved within decades of their discovery. Dark matter has persisted as an open question for nearly 100 years. And while the evidence for its existence has grown from tentative to overwhelming, the question of what it is has remained unanswered through the efforts of thousands of physicists and astronomers and the expenditure of billions of dollars in detector technology. This persistence is not a failure. It is a measure of how genuinely strange dark matter is, how far outside the ordinary range of physical phenomena it sits. We have been searching for it with instruments built on the assumption that it resembles the kinds of matter we already know, particles that interact through one or another of the known forces, and the possibility that it is something different enough from all known particles that our current instruments are simply the wrong tools for the job cannot be ruled out. The history of science contains many examples of phenomena that resisted understanding for long periods, not because they were incomprehensible in principle, but because the right conceptual framework had not yet been invented. Dark matter may be waiting for a framework that does not yet exist, for a generation of physicists who will look back on our current searches the way we look back on 18th century attempts to understand heat in terms of a fluid called caloric, sincere and sophisticated and systematically wrong in a way that could only be resolved by a deeper reconception. And yet, this uncertainty is itself a kind of gift. The universe has held its deepest secret with remarkable patience, revealing its existence from every direction while withholding its nature, keeping the most profound question in modern physics genuinely open. There is something luminous in that sustained mystery, something that keeps the most fundamental questions alive and the most careful minds engaged. We are living through the era in which the answer may finally come, and that too is something worth carrying into the quiet of a dark room and letting rest beside you as you fall asleep. The beauty of the dark matter mystery lies partly in its scale. Every other great unanswered question in physics is about something small, the structure of particles at energies not yet reached by accelerators, the behavior of space-time at the Planck scale, the origin of the asymmetry between matter and antimatter. Dark matter is a mystery about something enormous, about the dominant component of all the matter in the observable universe, about the substance that holds galaxies together and shapes the cosmic web and has been present since the first moments of time. It is a mystery written in the largest possible handwriting, visible in the motions of galaxies and in the bending of light across millions of light years, and yet utterly resistant to our most sensitive instruments. There is something almost noble in that combination of scale and elusiveness, something that speaks to the depth of the universe's capacity to surprise. We have mapped the genome, split the atom, detected gravitational waves from merging black holes 1 billion light years away, landed spacecraft on other planets, and decoded the light from the first stars. And we still do not know what most of the matter in the universe is. That not knowing, held alongside all the knowing, is one of the most honest and luminous portraits of where science actually stands. Extraordinary in its achievements, genuinely humble before the largest questions, and always, patiently, reaching further into the dark. As we come to the end of our journey, we have drifted through the invisible architecture of the universe and learned to recognize the shape of what cannot be seen. We have followed the motions of galaxies whose stars move too fast, watched light bend around matter that emits none, and rested at the edge of experiments so quiet and so sensitive that they can hear the universe's silences better than almost anything else we have built. We have traced the patient work of a century of science, from Zwicky in the 1930s to Rubin in the 1970s, to the experiments being run tonight in mines and mountain tunnels and university laboratories across the world, building an understanding of something that has never directly announced itself. We have moved from the scale of individual galaxies spinning in their halos to the scale of the cosmic web, that vast and luminous structure woven on an invisible framework, and we have found in all of it the same patient, pervasive, ancient presence. We have sat with one of the great open questions of science and found in its openness not frustration, but possibility. We have let the mystery carry us, and in the carrying perhaps the day has grown quieter, and the distance between here and sleep has shortened to almost nothing. If you enjoyed this journey, you might like to tap like or subscribe, or leave a comment with the part that surprised you most. It helps the channel reach more curious minds, and it keeps these long night voyages going. Let the shoulders drop now, softly and without effort, releasing whatever they have been carrying through the day. Let the weight of the body sink a little further into wherever it rests, giving that weight fully, without reserve, to whatever is beneath. The breathing is already finding its own unhurried rhythm. There is no need to manage it or direct it or approve of it. It simply continues, as it has continued through every night of your life, patient and reliable, and requiring nothing from the thinking mind. The thoughts that came with you tonight are growing lighter now, drifting a little further apart, losing their urgency, losing their edges. becoming something more like weather moving through than like conclusions waiting for answers. The invisible river of dark matter flows through the room right now, through the walls, through the floor, through the earth beneath you, as it has flowed through every place you have ever been, through every room you have ever slept in, through every landscape you have ever known, constant and unhurried and ancient. It does not slow. It does not notice. It has been flowing since before the sun existed, and it will continue long after the sun is gone, patient and vast and utterly undisturbed by anything that happens in the warm and luminous thin film of ordinary matter, where all of life unfolds. Let the quiet do its work. Let the night deepen around the edges of awareness. Let the thinking mind rest the way the body is already resting, loosely and without holding on. Rest is very close now. The darkness behind your eyes is the same darkness that fills the space between galaxies, vast and full of something invisible and ancient and patient. You are already very nearly there. Let the next breath carry you the rest of the way. Sleep well and good night. And if you happen to still be awake, there will be another video waiting on screen, ready to carry you onward into the night.